Hey everyone, thank you for joining us today. And today we are very fortunate to have Sarah to give us a talk here. So I don't like Sarah does not need a lot of introductions. I'm just going to keep it short. But she leads Go here for AI and has been doing really great work in the multilingual LLM space, but also bringing out great machine learning algorithms for LLMs itself. Apart, she was also back at the Google Brain before this, and where she did a lot of interesting work. And like her general areas are still interpretability, efficiency, robustness, and apart from the multilingual research that she's carrying out today. So she'll talk to us a lot about these things already. She's also serving on Kaggle's ML Advisory Research Board, as well as the World Economic Forum Council for the Future of AI. So with no more further ado, I will just hand the stage to Sarah here. Let's just
Yeah, it's really lovely to be here. And yeah, I prepared a talk. There was more things that I've been thinking about for a while, some of the general themes. So some of this I think is, oh, so I'll bring this back. Got it. Okay. Okay, here we go. Yeah. So some of these themes are, so I lead Cohere for AI, so you may have heard of it, but we're Fundamental Research Lab. We work on both releasing many of our insights, as well as we do a lot of cross-institutional collaboration. So I'll just share some of these are in areas like efficiency, LLMs at scale, safety, multilingual, hardware-software interaction. And I won't talk explicitly about multilingual today, but we also do a lot of work on multilingual. So we've released iExpanse, which is really state of art in modeling these 23 languages. I think this came across in some of the questions before the talk as well. Um, and maybe the last thing I'll say is any of these topics, I'm talking mainly today about how I see a larger trend, but any of these topics I'm happy to chat about after the talks. I think we'll have some time. So we can use discussion then. And feel free, I'll also be asking, kind of creating some moments where we can have more kind of question back and forth during the talk. So feel free to jump in. But today I thought I would talk about this paper, which I released last year, which was on the diminishing returns to scaling. So this was actually, I rarely have the time to write anymore, but I took the time with this one because I felt it was fairly important. I think there's, in some ways, a wider question we've been battling as a field, which is what is the primary ingredient for progress? And I'll talk about that today, and I think we can have a nice discussion about it. So firstly, I'll talk about what the role of capacity is, and then promising directions of research. I won't be talking about multilingual, but so we can just scratch that last box off. But I think we'll have enough for the first two, and we can see if we have time to get to other topics. So what is the role of model scale in data and recent breakthroughs? Who wants to give it a go? Yeah, go for it.
emergence of new skills which the model previously did not have.
Yeah, so emergent properties. Who know, I guess what is the definition of an emergent property as we've seen in the literature?
I mean, a kind of a skill which did not work on smaller scales, or
Yes.
but you suddenly see
Yeah.
a high score or high evaluation.
Yeah, so emergent properties have emerged as like a motivation to scale. So the premise being that there's certain properties that won't be visible unless you scale compute. And then they were often called emergent or surprising properties because the early ways of modeling them showed a sudden uptick. That's an open question now. We can talk about that because if you use different ways of modeling this, it's less abrupt. But you're right. They're one of the motivators for like this bigger is better race and model parameters has been like this belief that maybe there's certain scales at which there's new properties or behaviors emerge. And we can see that this is in very much a dramatic uptick in terms of scaling. Why else? Why else have we scaled so much? Go for it.
It's the safest bet to, I guess, like for all these companies, it's the safest thing they could do to continue improving their models, just to scale.
100%. It's a very predictable formula in some ways. It's like, I guess it's hard to deviate. It's hard to justify deviating. It also typically fits within a quarterly cadence. You can say, let's just try and increase the model, and then you can see the results. So it's a painfully simple formula, which makes it hard to argue against. The only cost is money, but we can talk about that as a separate topic. Yeah, but why else? So one is a simple formula, the other being like there has been empirical evidence to show it's successful. Why else are we obsessed with scaling? Our current architectures are also quite scalable. Like there's a question now about what are the limits of that, but one of the key advantages of the transformer was that it was more parallelizable. And so there was now this sharper gradient of scalability that you could exploit compared to convolutional neural networks. So it's worthwhile also thinking about that ingredient as well. Um, yeah, so this characterizes both vision and OP tasks. This is like an overall trend that is dominated, and it involves large increases in both model and data set sizes. So we've seen overall this really strong belief in bigger is better. This is captured by Rich Sutton as the bitter lesson. So Rich says the only thing that matters in the long run is leveraging of compute. And this is kind of a punch to the ego of every computer scientist out there, because what he's really saying is that a lot of the fancy things we do don't matter. What matters is letting a model learn parameters for itself, coupled with scaling of the algorithm. So who agrees with this?
Some extent, yes.
Okay, excellent. Love it. Yes, nice one.
I don't know. It's just like in some ways Occam's razor, like whatever, like you can do a simple thing that works, but you just have to do it at scale to get it to work in the same way that you want it to work. I'm not saying it's the smartest way, but it's the simplest way. So it can definitely work.
That's certainly true. I think for some, so it's nice. An example that could support that point is something like unsupervised pre-training, essentially. So it's very simple objective. It's very crude, and it only really works when you have enough data to make it meaningful to learn the structure. So unsupervised techniques in general, you require a lot more data to get the same signal. Yeah, what else? Who believes? So you had your hand up. Anyone else think this is yeah.
I guess just like in machine learning itself, like with the idea of the model learning on its own, like we've developed different ways to try and guide it, but in the end, what we really need is to just let it run and run and figure it out on its own, and that's like the paradigm that we've built for now.
Oh, let AGI loose. Is that captured? Okay, nice. Who doesn't agree with really just fit a lesson, and why? Yeah. Okay, a few. Nice. So maybe let's go here first and then.
Okay, because I think humans are very good at making inference from smaller data.
Yeah.
So which doesn't necessarily mean the more data is the better, or to take resources better. So I feel like maybe a better solution by approximating human solving.
Yeah. Yeah, that's true. So it takes us very little computational power to process a lot of information. That's largely I mean, there's a few reasons. We have very nice ways of discarding a lot of information, but our current models, at least the ones we've chosen, they are very inefficient and very data hungry. And so it's quite interesting. Yeah, it's a very nice point. Yeah, what else?
Yeah, that's something very similar to that. I think the architectures and the methods we have, they do very well for certain tasks.
Yeah.
But I think once we start to think of fairness, inclusiveness, the different languages and stuff, the data size, I don't think that this architecture that we have is the way to go. So we need to come up with, we the data scientists, computer scientists need to come up with better ways of building better algorithms that can leverage less data, less compute to have better outcomes or same things.
Yeah, I mean, our current architectures are all based on empirical risk minimization, which means average error, which means that takes a long time to learn the long tail, because it takes a long time until the lowest frequency are the parts of the error that need to be reduced. Yeah, excellent. What else? Anyone else here wants to take the counter position or wants to support Rich Sutton? Okay, okay, maybe here first and then there.
Yeah, it's the difference. Back in a few years ago, I think when people are all focusing on the general performance of the task, I think simply increasing the amount of parameters can increase that a lot. Right now, I think we are really thinking about deploying AI.
Yeah.
other side, safety, privacy, those stuff. And I think those we actually need to come up with other algorithms like that instead of just bring up values.
Yeah, there's hard constraints in the real world. So let's say you want privacy, then you are thinking of a private deployment. You're much more constrained in the size of architecture you can deploy realistically. Yeah, so very nice point. Yeah.
Yeah, to kind of support, I think, better last time, I know I might be saying like completely not, but when I like think of language, like even the English language is just so complex and people spend like years learning linguists. We talk about like how we're able to infer stuff on small data sets, but I don't think like brains can comprehend like the vastness of like the data that's sometimes hard maybe for us to like pick very like at least from what we learned, what I learned in probability and statistics, we have these nice general models that, for maybe most of this data it works, but it's hard for like to capture everything. And I think maybe with like scaling and having as big as you can, you just are able to capture all these like complexities that it's just hard to like wrap in one nice little mathematical model.
So that would be a bullish view. Nice. Okay, good. We have a good mix. Yes, go ahead.
I think I would point
Do you know each other? No.
I feel in some ways there's been a lot like of using ability of reasoning, understanding text as like proxy for ability.
Yeah.
I think with other applications, particularly safety or potentially actually interacting with other systems, so like an actual computer system, in some ways, I feel like we are going to have to develop better techniques rather than just throwing more compute at the problem.
Yeah. Yeah. Okay, fine. This gives us something to start with. Okay, let's go for it. So is said and right. So I think this was highlighted in a few of the conversations. There is an argument in favor of this approach. So the notion of overfitting to our beloved notion, traditional notion of overfitting has been cast out the window in some ways. This idea that you can scale and still end up in a useful regime of generalization is one of the key things that has been motivating some of the scaling behavior over the last few years. And also, as was pointed out, it's an extremely simple formula, which means it's hard to deviate from, even though it kind of turns us into hardware architects, because we're now following our own Moore's law of being stuck in very boring research regimes. And then, of course, it was talked about like this emergent properties, and we do see some of this. Like we see that this is now more controversial, the idea that it's surprising. Because I think there's been excellent work out of Stanford, which shows that these modeling curves are maybe not the way you should model some of these departures, and it's much more gradual. But there is consensus that, scores go up as you scale. And there's some techniques that we really enjoy that require larger and larger models to take advantage of. So instruction tuning works very well if it can exploit a base. There's similar arguments being made about reasoning models, the ones that have just been released, is that you need a very strong base quality to be able to leverage reasoning. So this is another argument in the favor of scaling. So for example, DeepSeek is being portrayed as like a very budget conscious model, but it is above 600 billion parameters. And so there's an argument or a question mark within the open discussion of like, how big does your base model have to do to induce some of these downstream behaviors? So I think these are all nice problems that have kind of come up in this discussion. I think a key limitation is that the relationship between weights and generalization is really not well understood. And this is from a few perspectives. So models of the same capacity became much more powerful over time. So these are like models that are under 13B on the LLM open leaderboard on Hugging Face. And it's the best daily model under 13B. And these are larger models that are outperformed by these best daily models. And so we see over time, there's just much more large models that are not particularly performant. So scale is not in itself enough. There has to be a combination of scale and technique. In fact, we kind of observe a highly uncertain relationship between compute and performance. And I'll share a few kind of key ideas here. So what is that? It's very clear data quality compensates for the need for compute. Why do I say it's very clear? What do I mean by that? If it's not very clear, then I can. Well, what do I mean? Go for it.
In general, internet speed is not really good. So
It's right, yeah.
we need a lot of compute to look for the patterns that the model is trying to do.
Yeah. So this is a very good. So internet data contains a lot of garbage. And so yeah, it's a. I think what you're saying is the hypothesis of why we need so much compute for pre-training is to deal with the regularization that garbage introduces. Very nice. What else? What empirical evidence do we have that data quality matters? I would say, oh, go ahead. Nice, go for it.
No, I was just going on the lines of post-training of preference.
Yes, precisely. Bravo. Nice. Well, yeah, I think what's being got at here is that think about what IFT is in our modern regime. The difference from pre-training data is only structure. It's structuring data so it's close to the distribution you expect in a chatbot, which is super fascinating if you think about it. And so you get away with less data, but it's just in the structure as closer to your end distribution. Same with preference training. It's much less data at that stage, but it's more structured in the way that you want through optimization. And so it's quite interesting once you think about it through that lens. And so we know also that even if you think about internet data, there's a lot of pruning techniques you can do to do more with less, right? So we've done work on this, but it's there's a lot of now studies which show deduping, pruning data, synthetic data, investments there pay outsized dividends in terms of allowing you to go smaller. Our recent work, this was led by Max. He was a scholar part of our program. We really did this at pre-training scale. So this was extremely large scale data pruning, and you have to use very cheap scores to estimate quality because of the scale. But we showed that you can get away with training on as little as 30% of the original data set. And that's largely because of quality issues. So precisely what was being said before. And it's interesting because this is valuable at multiple stages of optimization. So we had other work, this was led by Miriam, where you kind of reduce the number of indecisive outcomes with data annotation by prioritizing what is shown, like the most uncertain examples to be shown. But the second point is that I think compute does not capture the algorithmic breakthroughs that have led to large gains in performance over the last 5 years. What are some of those breakthroughs? We've had one, preference training. Yeah, what else? So what are some optimization techniques that don't require more compute necessarily, or require very little compute, but dramatically improve performance? Pardon? Laura, very bravo. I like that. That's nice. They technically do introduce new weights, but like it's very interesting because it's very little and it kind of it's on the fly. So yeah, you can argue that's an efficient way of introducing new data. Nice. What else? You can also sometimes, yeah, that's interesting. Yeah, go for it.
I mean, I don't completely agree with this, but like
Oh.
mixture of experts. No, not with this, but with my answer, what I meant.
Oh.
Like mixture of experts itself, like in the sense of
Mixture of experts is definitely a different use of technique of compute. Yeah, you're going wide instead of deep. So maybe it's a bit of a weird answer because you are still technically very large. You're just using your capacity differently, but it is adaptive compute, which is interesting. Yeah. What else? Okay, here and then here.
Multiple dots.
Oh, fun. Fun. So typically multimodal approaches today have involved more weights, but not much more weights. It's been kind of interesting so far. I think that's partly because we're normally tacking on Frankenstein style, like multimodal right now. I think the longer trend is multimodal models will require more weights because we'll try and optimize jointly from the beginning. But still, yeah, it's kind of interesting. Yeah, I haven't seen much work around evaluating typically the goal of the multimodal is to preserve performance while adding in additional sources. But you're right, if it is more like our own intelligence, it should actually lift all boats. Like having audio, vision, a tactile actually helps us improve our overall estimates. So you're right that I think that's the vision. Yeah. Yeah. What else? But okay, maybe I'll frame it differently. And this is a bingo card. What costs zero compute but it can increase performance? Okay, go. You're ready. Yeah, go for it.
The recent breakthroughs have been around counting.
Yes, go for it. Yes.
different ways like chain of thought.
Yes, bravo. Okay, there's a lot of bingo cards. Nice. Good chain of thought, prompting, nice. What else?
And probably also innovations in MLSys, like flash attention, VLLMs.
Oh, very good. Yes. So architecture improvements. And bravo for being the first virtual person to chime in. Very good. Yeah. So I completely agree. I think things like improvements to architecture that make it more efficient, that could count. Yeah. Technically, you're not adding more weights, you're just dramatically improving the type of, ways that the compute is used. Yeah. Anything else here?
I mean, like distillation.
Distillation. So it's kind of interesting because it is compute, but it tends to trade off. It's inference time compute, which trades off with training compute. Yeah. Anything else? Okay. I'd say there's a few, right? So even something like tool use is technically it's no more compute, but it can dramatically increase the performance of the model. Best event sampling and distillation are examples of additional compute, but it's placed in a different part of your training process, and it reduces the need for the size of your model. But there's things like RAG and increasing context length that are often close to free in terms of increased compute, but dramatically improve performance. And multitask training. So even our shift towards universal models, that's been a dramatic improvement, but has cost relative to pre-training very few flops. And I think something like multitask pre-training is really the shift towards a single model. But all three have relatively limited compute cost compared to all the flops you spend during pre-training, which is enormous. Like your bulk of your compute project is spent in pre-training, but then when you get these shifts towards different techniques, which are closer to your distribution, you have much less data and you spend much less flops. I think this is largely kind of some of what we talked about before, is that we're battling the fact that we've actually moved away from a traditional machine learning problem. In a traditional machine learning problem, you sample IID or your assumption is it's representative of your test distribution, what you want to actually represent at the end of the day. But with the internet, it's not actually a sample that's representative of what we want to the model to serve at the end of the day. So we spend all this time and a huge amount of compute trying to get closer to that distribution. But it's interesting because once we have the data that is more close to that distribution, it becomes a lot less compute intensive. The tricky thing is that data is hard to obtain. And so it's very interesting. But I see this entire training path as becoming more cohesive over time. As we get more data in the format that we actually want to deploy to, the notion of pre-training, I think, will become, this is going to be seen as a temporary stage in a hack to try and get at this. And then I think that the combination of these techniques often has combined positive effects. So instruction training and multitask training improves performance. Preference training on top improves performance. I think this was IA 23. So this was led by John Deng, who is actually at UCLA. Now he's working with our lab. And this was actually before IA Expanse. So this was applying preference training. Our focus was really on how do you do it for multilingual. But I will say, that first kind of set of techniques was all about how do you get the data closer to the distribution. There's also a really interesting shift where now we can do things post-training to really condition the generation space or to create data to optimize in the data space. And some of these are free. So increasing context length, as long as you train to do it, you can add a lot of information in context. Same with RAG. But best event sampling, chain of thought, nice finger card. RAG, models-enabled tool use, these are all very cheap. And so this is a dramatic departure from Rich Sutton's lesson, because we are no longer in the purely algorithm model-focused space. The way that some of these techniques interact is after training, which is frankly a departure from how our field has treated even training computer scientists and doing a PhD. We now have this much more expanded view of ways that we can shape the optimization process. So the other thing I'll say, another possible counterpoint to Rich Sutton is that the relationship is not well understood between weights and performance. So this will be a nice classical chart, even though it's only from 2018. This was the difference between Inception v3 and Inception v4. So this is a computer vision architecture, convolutional neural networks. And convolutional neural networks were our last architecture to saturate. So when you go from Inception v3 to v4, you double the number of weights, the number of parameters. And this might seem quaint because it's only 21 million to 41 million. So we're not in the era of billions yet. This is before the transformer crazy scaling. But what's interesting is you can already see the trends of saturation. So all that for only a 2% gain. So typically architectures unlock a new search space, and then we end up saturating that search space when we kind of scale within it. And we see the same, I think, with the transformer now. We're starting to see the same limits of saturation of architecture. But this is very natural. In fact, it's kind of expected. All this is doing is conditioning a search space. And we often see the big breakthrough is a new architecture, which creates a new search space we can exploit. But not only do we see this decreasing returns of weights, and so it's unclear how long we should just scale in the industry way of like new quarter, bigger model, but also there's a lot of redundancies between weights. So this is a lovely paper. I think this is the exact type of paper that's often very, is quite charming when you read it because they do a very simple experiment. They're just showing, this is from Nando's group. They find that just a small set of weights can be used to predict 95% of the weights in the network. So all our weights are very correlated. And that's why we can prune. So this is work I did while I was at Google, but sparsity in general, we see these trends frequently. You can tolerate massive levels of sparsity in these networks. And so even if you randomly prune, so no precision about what you're pruning, you can get up to 90% without dramatic decreases in performance. Go ahead.
So even though people, I think, try to reproduce the 2014 paper from the more recent architecture and like
Oh, these techniques?
Yeah, I mean the previous paper.
Oh, okay.
Is the
no, yeah, it's worthwhile doing. I mean, I think that we can still. So probably a corollary of this is how easily can you sparsify or quantize, and we can still do it fairly easily without much degradation. So I suspect some of this still holds true, but I don't know if anyone's tried it. Yeah. So does anyone know if someone's tried this paper? Scaled on transformers?
I think NVIDIA's Nemotron breaks down the largest llama using pruning, and then they fine tune the smallest. So basically, they first start with a big llama, then they prune it, and then they fine tune it with a very less distillation data.
Oh, I see. So like lottery ticket hypothesis reversed. like they first train a large, then they find the lottery ticket subset, then they train that again. Is that the idea?
Yes, and they don't even train the largest model. They start with Llama 370B or something.
Okay, interesting. There might be a bit different from I think your question, which is asking, the degree of correlation, but I do think that they may be intertwined. But I do like that example. That's fun. And then, so in addition to knowing that we can throw away most of these weights once we've trained, which says that why do we need them in the first place if we can throw a lot of them away? There's a question about what is lost when we throw away these weights. So a lot of the research I did over the last 5 years was about this, like what do we lose or gain when we dramatically vary capacity? And this is an important question because it kind of gets to the heart of what are we doing when we scale. So we looked at this in many different settings. So one is really just thinking about it with this idea of like both computer vision, NLP, but also under different constraints like sparsity quantization, very popular efficiency techniques. And a lot of what we did was, I guess I'm just, so there's some very nice work also for low resource languages and when we looked at quantization as well. But I'll share kind of the top line findings. So what we found was when you vary capacity dramatically, a subset of the distribution is disproportionately impacted. So this is the part of the distribution that's most sensitive to scale. Then most improves when you scale, and there's the first to be lost when you compress. We call this pre-identified examples, and these are really the most sensitive. And I'll show you some examples. So what is the true label of this image? I like the smile in the back row. Yeah, sounds like you're ready to guess. Yeah. What do we think? A plane? A plate? A plate? So this is a toilet seat. So this is pi and non-pi. What about this one? What's a wine glass? A wine glass. So this is espresso. Technically, it is also a wine glass. So good hedging of the estimate. Yeah. What about this? It's a game. That's actually very close. It's a maze. What about this one? So, oh, I guess that doesn't. So this is actually wool, the true label. And this is an example of matchstick of pi non-pi. And you may have gathered by now that these are quite difficult examples, even for a human. And actually, we did a human evaluation, kind of codifying what these examples were. And we found that they over-index on two groups. One is noisy data points, and the other is atypical data points. And in many ways, you can think of these as two different really motivations for scaling. So we never want to use more capacity to represent bad data points. This is bad memorization. We're essentially regularizing our model by learning these data points because they're not learnable. But then we have these long tail or atypical data points, and we want to use more capacity there to represent these data points. These are some examples of noisy pies. So it's interesting you said wine glass is the guess because many ImageNet images have multiple possible labels. So for example, here the true label is desktop, the non-prune label is screen, and the prune label is monitor, and all three classes are legitimate. And so here it's an issue. The issue is we've treated this as a single class classification problem, but in fact, many classes can be true at the same time. The same goes for like wine bottle, red wine bottle, groom, suit. But also there's very noisy examples. And so we replicated these studies, of course, like across both computer vision and NLP, and we see the same across both. Like you over-index when you're sensitive to capacity, is that when you scale, you get better noisy and atypical. And so some of these are things like it's not possible to infer the restaurant from this image. It's very difficult to infer envelope as a topic for the second image. And then the true label of tub, cauldron, wok. Atypical data points have an unusual vantage point or example. So for example, here might be a toilet seat, but maybe added distribution, bathtub, but plastic bag. These are all valid labels, but they're unusual examples. And what this means is that, frankly, this is also a symptom of the fact that we use scale to learn these is a symptom of our optimization approach, right? We're using global batch updates, so it means it takes more capacity or longer training to reach the long tail. We want to reach the long tail, so we also learn the noise, which regularizes our capacity. So we need more and more capacity, the more noise we believe we have in our data set. Internet is probably the best example of this. A lot of the internet is junk, so it just regularizes our learning. So our response is to scale. And the interesting thing is the majority of features are learned extremely early on in training, like extremely early on. Like most of your pre-training is spent learning the long tail, but most of the most coherent features you see emerge almost immediately. Like after you, it probably like within the 5 to 8% of your overall pre-training time. And the majority of features can be learned using small models. So scaling of size primarily impacts a very tiny part of your overall distribution, which is crazy when you think about it, right? Because we spend just a huge amount of effort and compute and infrastructure to learn a very tiny part of the distribution. So this prompts a question of where do we go from here? I'll share some of the directions we're thinking about and we're working on. But it really gets to the hardest question, how do we make better use of capacity and how do we buy the cost of representing the long tail? I'm going to talk about 3 directions that I think could be fun and we're working on. One is just optimizing in the data space, so data pruning or weighting. So I call it spending more time on the data you care about. So here we've done a lot of work on like how do you efficiently prune and how do you score quickly large amounts of data. But I think even more exciting, last year we did a lot of work around just optimizing in the data space. So for most of computer science history, we've treated the data set as fixed, right? It's very expensive to collect, it takes a ton of effort. And so we largely treat it like I showed, ImageNet as like it's given to us, and we just do everything we can with the algorithm around it. But that's not true anymore. So now it's possible to create high quality synthetic data, at least for parts of our distribution, but in a much more cheap way than data collection has been in the past. But this opens up the door for steering the properties you want in the data space, for kind of hacking this empirical risk minimization by creating a stratified example of where we want to go. This is actually huge. It means that our space for optimization is much broader. And in particular, so with this second paper, LLM-C, LLM-Do, we showed that you can even steer towards non-differentiable objectives. So we can use metrics that haven't been used within our most popular models for a long time by using them implicitly to guide how we optimize synthetic data. So this is super exciting as a direction. I think the other is really, I think what was mentioned before with mixture of experts, specialized or adaptive compute. We've done a lot of work around this. We've also done work around mixture of experts. We've done work around adding, especially a compute constrained mixture of experts, so adapters, which are mixture of experts, but also even on the pre-training side. So like, how do you create enough data diversity? I will say, like, I think adaptive compute goes beyond this. I think there's very interesting directions. The main trickiness about mixture of experts is they're very unstable to optimize. So it's very difficult to get them to, especially at scale, to get a stable kind of convergence path. And they don't really get a true modularity. So if you really look at a lot of mixture of experts papers, you end up having to really squint to believe they're doing something that's specialized, because most experts end up learning very similar things. So I think there's a lot of work there. I think there's also just interesting directions around like learning routing on the fly. But happy to talk about that. And then, I guess I go into more detail, but I talked about this, data pruning. Feel free to look at these papers afterwards. I think reprioritizing examples. So we've done a lot of work around leveraging early training signal. So since most of the most common features are learned very early on training, can we leverage that signal as we go? So just to stop treating training as like, I press go and then I come back in a week or so to see how the run is doing, like to start treating it as like an active intervention point. So if we can leverage early training signal, we can adapt the composition of the train set on the fly. I think this is really interesting. And then high quality synthetic data. So one thing, because we've done so much work on multilingual, we've explored a lot of different optimization techniques around synthetic data, especially on sampling techniques, reducing uncertainty by essentially spending more compute sampling from the same model multiple times, but also more sophisticated strategies like multilingual arbitrage, where you have a pool of teachers and they may be specialized in different things, and then you're getting variety by changing either the hyperparameters of which you sample or the pool from which you sample. And I mentioned this, but I think this is a very nice piece of work that starts to get this idea of steering the data space. And typically, I think this has also been a theme that's been surprisingly talked about in a way that is a bit confusing in the general population. So the idea that synthetic data has mode collapse, I think relies on the assumption that you're just for generation after generation resampling from the same teacher. This is I think it's a nice edge case, but I think that it's much more interesting to think about the ways to avoid mode collapse and to preserve diversity in your teacher setting. And what we found is that if you can preserve diversity, you can get much more interesting patterns within your data distribution. Okay, and then specialized adaptive. Okay, so I've talked to you a little bit about this, but I think this really gets to the idea of spending more time with the data points that you care about. So it's good memorization. And mixture of experts is one, but I think there's also others. I'm going to open up here. I think it would be nice to do some more open discussion. I'll probably end with this. I think we've only existed as a field for 77 years. So in some ways, it's wide open, the tooling that we use. And deep neural networks are clearly not the final resting spot. So I actually suspect this will be a very interesting chapter as we really wrestle with these expanded optimization spaces that typically were not really the center of our field. But I think it's very clear that the next breakthrough may require a fundamentally different way of modeling the world. This also, we haven't talked about in this talk, but I often think about hardware. I think that in many ways, our hardware and software has become increasingly overfit to transformers, which makes it much harder to deviate. We're kind of in the middle of a very sticky tooling stack, and we're very much in a setting where, because we've moved to domain specialized hardware, it's really overfit to one component, which is matrix multipliers. And this is something we shouldn't underestimate. It's made it very sticky to deviate, and we have to think about what this means for, finding what's next. And I think it means that we should justify additional complexity and bend scaling layers by focusing on efficiency. So this is one of our key research bets. But with that, I have talked a bit about this. I think it's an exciting time. Yeah, let me leave it there. Let me open up. What are questions that people have?
I guess I have a specific question where the slide about multi-unit arbitrage.
Oh, yeah.
Where you were discussing mode collapse.
Yeah.
But wouldn't all these models, like in this, I guess what you would call the arbitrage pool, wouldn't all these models be facing pretty similar mode collapses? And as a result, like, because they've been trained, especially in the context of, say, different languages or whatever, they've been trained on similar distributions of language and almost likely identical data as well. I guess it's this question very specifically related to this paper.
Yeah, I actually don't think so. Remember, you have different data mixes for different models and different language coverage. And so I think it's interesting. So this was an academic setting we did this in, so we released this paper, but we did another setting where we actually trained our own geospecialized models because we wanted full control of the data mixture. And also because that was a setting that we really used to inform IA Expanse. And there we really focused on there being regional experts in some languages. But even so, sampling from all the experts, despite some not having as good coverage, ended up improving overall diversity. We also see this, think about classic ensemble literature. Like, you can even ensemble the same architecture, train on the same data and see gains. Typically, stochasticity used in training, stochasticity and data selection, these compound over the course of training, and you still get major benefits from having a pool of essentially ways to estimate what is better. I think that the notion of mode collapse, it really hinges on the idea that you are sampling the same distribution, but you're also training the model each time. So you're sampling from a more narrow distribution over time. There's no doubt, and what we saw in the other papers is that if you only sample from one model, you're inheriting exactly that model's biases, and you are oversampling from the mean of the distribution, from the mode, right? Because you're not capturing the long tail. So that's all true. But you can mitigate that by also deciding what is the best model to sample this language from versus that. And then that changes your distribution. So you can be more selective about what you build your distribution from. Yeah, that's a nice question. What else? Yeah, go for it.
Yeah, so you spoke about small models, big models, and mixture of expert models. Something interesting I'm interested to hear about is model merging. You didn't mention Frankenstein, but that's something.
Yeah.
But what do you think about the role of model merging these, getting efficiency for tail and task and languages in general?
I think it can be very effective. So we released, I think, 2 papers on model merging late last year. So we have shared publicly about this. And we show massive gains. So particularly the balance is you want your merge mate, your different candidate models to merge, to have some shared basis of learning, but some differences. And so that allows for some stability in the merging because you don't want your weights to be dramatically different in weight space. You're kind of interpolating in weight space. But you do want enough distinction where you can incorporate properties. So, for example, one of the papers we released was focused on safety. We had a model which essentially was aligned to more local notions of safety, meaning that these were annotations by in-language speakers based on their notions of local harm. And another model that was aligned to more global notions of safety. Think of it as like violence against yourself or against others, things like that that are more universal in terms of how legal frameworks treat them. And when we merged, we found benefits for both. So like it kind of raised all boats. And part of this is that you're finding more interesting spaces and weight space where you can like end up in a better overall performance. But what's nice about merging, and what I think is often underappreciated about it, is that is one of the cheapest interventions you can do. So there's a lot more space there to over optimize. So you can imagine if you have a massive pool of models, which most industry labs or even researchers at the end of experiment have because they've done so many ablations, you can now be in the area where you can do a much more aggressive search about what's the best combination, which is interesting. Yeah, really nice. What else? And what time is that? I want to make sure I'm.
We have time.
Okay, good. Yeah, go ahead.
You mentioned before the discussion about getting unlocked in this hardware technology. Do you see any potential alternatives that are worth exploring in both the hardware and software stacks for techniques or other potential avenues?
Yeah, I mean, one thing is that the software side is easier to talk about, right? The hardware side, I think, is very difficult because there was a period about 4 years ago, maybe 5, where there were a lot of hardware startups getting funding that were doing interesting things, like Cerebras, which was a single wafer, very cool. But they've almost all reverted to like optimizing for matrix multipliers. So I think many of them have realized just the cost of hardware ideation have now really narrowed in to do really well at the most popular networks. The software side, I think we should push more, and that it feels more tractable to more aggressively vocalize this, is that the software, the main issue is a lack of portability. So even if we could make software more portable, we could try on more different devices more easily. Right now, about 40% of PyTorch functions don't function on TPUs, and the remaining show massive slowdown. The opposite is also true. Typically, TPU, like TensorFlow, JAX functions show massive slowdowns when ported to PyTorch. So that's, I think, a very tangible thing where right now researchers basically choose their stack and don't deviate from it. But different frameworks allow for different types of idea implementation. With JAX, it's very hard. There's elements that are iterative, but it's very much still a graph-based library. And so it's very hard to modify the architecture on the fly. It's very hard to change your batch characteristics on the fly, but it scales better. But what I'm saying is if you think about something like adaptive compute, even something like early exiting, it's not possible in JAX because the whole model is already being loaded into memory. So even if you were to do early exiting, it's no memory savings. So it's kind of interesting. There's these things that we need to sort out. The hardware layer side, I'm honestly a bit disheartened by it. It's almost becoming the emphasis on efficiency and this coincidence of transformers being at the edge of research, but also widely deployed in the real world has meant that there's not much incentive to stray from transformer optimization. And it doesn't bode well for what comes next. Because if you think about it, there's many reasons why we want to deviate from essentially optimizing for matrix multiplies. Even this idea that maybe you want to do better at sparse, more dynamic networks that can grow or that can adapt. These are very interesting areas that are unlikely to come to fruition within the next decade because of how hard it is to get empirical support. Yeah.
You use a lot of TPUs, right?
We actually use both. We use different stages of training for different hardware stacks.
But
yeah.
I mean, you guys don't do PyTorch much. If you have.
We do, yeah, we do, but it's painful actually. That's one of the reasons I'm so aware of this discrepancy is that we do some optimization processes on TPUs, others on GPUs. And so that conversion process is also fun. Yeah, very cool. Yeah, go ahead.
Face off speculative decoding to functions here, and it's shortcomings and real world users.
Oh, interesting. I don't know. I haven't done much work on speculative decoding. I think sometimes the benchmarks we're using to evaluate speculative decoding don't really take into account that it must have much worse performance on the long tail. I mean, if you think about it, some of those popular techniques for speculative decoding involve kind of using smaller models or drafter models to kind of refine and make it more quicker. You can imagine those models are probably good at the most common use cases, but not at the edge use cases. So yeah, are you doing research on it? Maybe you probably have a better framed perspective. The driver of speculative decoding, for those not working on it, is just efficiency, especially efficiency at kind of serving time. But I think the trade-offs are not well measured right now. Yeah, so I actually think it'll be very fun to have. We have done some work on the effectiveness of multilingual and it is pronounced, but there's other use cases that I think can be better studied and discussed about. Yeah, really nice.
So you said speculative decoding that really hurts multilingual performance because it's long tail.
It does, yeah. At least, so this is work which hasn't been released yet, but I believe will shortly. Yeah, so I think that this is a cross-institutional collaboration, so it's actually a PhD student who's working on this. But in many ways, I think there's a broader class that it will probably impact, and you can understand intuitively why. For speculative decoding to have the latency gains, the model has to be smaller than the actual model. And so if you think of it like that, then you can start to understand the implications for the long tail. Yeah. But I think a lot more is needed to specify the degree of disparate impact. So I definitely think if you're doing work on it, it's still a very important direction. Yeah. Sorry, I didn't mean to, because I'm like, I couldn't tell if people were working on this as well. So, but no, I think this is very preliminary work that this PhD student is doing, and much more work is needed to understand the impact of speculative decoding. So keep going if you're working on it. I saw some people exchanging eyes. Yeah, it's still needed. Still needed. Yeah, what else?
I have a question more on the building the smaller models or even quantizing bigger models to build more efficient models, but in the space of multilinguality. In the sense that, from what I understand, with scale of compute, we are better able to serve multilingual things as well. But as the compute gets smaller, the multilingual performance is also affected quite a bit. So it's kind of in the sense that we want to go small to make things deployable faster. And does it mean that we need to build more specialized models for specific languages, which can give higher, better performance compared to building a bigger, a highly multilingual model, but on a smaller scale?
Yeah, I mean, certainly there's a trade-off. So I think that now, I think I kind of alluded to this earlier, and I think it's important to understand that trade-off. So if you put 101 languages into a 7 billion parameter model, it's not going to be as performant as 23 languages in 7B. So you have to choose your balance, and the sweet spot is you get the cross-lingual benefits, but you don't avoid overstraining your capacity. Because remember, it's almost like multilingual is probably one of the most extreme multitask settings, because within multilingual, for every language, you want all your tasks to still be good. You want a coding model, you want all these aspects of what you already expect from English. So it's really the most extreme set of constraints. Yeah, but I am optimistic that with better data quality and with more optimization in terms of technique, you can have better regional models, like so languages that have good cross-lingual transfer, and you can get to the 3B, 7B stage. But that's kind of one of our, our North Stars, is we want to get to extremely performant multilingual for 3 billion parameter models. Yeah, go for it.
So I guess in the context of like cursor multilinguality, like when we were talking which is something that came up when we were with like XLMR, like models that were like way smaller, like in like 2019 or something like that. But now we're seeing these models which we even 7 billion parameter, like we believe like they're pretty sparse, especially relative to models like that. And so like even though the capacity of these models in theory should have gone up a lot more, that's being taken up maybe by different emerging capabilities or whatever. But do you not see like there being a very clear way of prioritizing or maybe separating like multilingual capabilities, given that there's potentially a good amount of sparsity in these, even at 7 billion parameter, like let alone bigger, and separating out maybe like places where there's these other capabilities that are maybe language agnostic versus like in the first couple layers, which in the first couple layers of a 7 billion parameter model, like that's the size of an XLMR or something like that, like where it was able to, you know, maybe not do that well, but it had like 100 languages, and was able to at least do something decently in all those languages.
I mean, XML is a bad example because it's a very academic model. And most people now would say that's not satisfying at all or doesn't fulfill what they want. The issue with XMLR is that typically, so at that point in the generation, you were giving very short responses, and it was primarily aimed at academic benchmarks. Our expectations are way, I think it's unfortunate that academic benchmarks are so in tension actually with open-ended generation properties that people like. So we have two different groups of benchmarks. What is open-ended generation, whether someone likes it, whether it's the right tone, whether it gives you the more kind of like verbose, complete answer. And then we have these academic benchmarks, which we still love, like MLU and kind of different pro versions or Redux or all these things. And it's actually kind of these benchmarks actually more intention than we think. So doing very well at academic style data set, you can do that, but you may not end up with the open-ended conversation ability that you want as well. Actually, a lot of post-training optimization is about balancing these two goals, which is kind of silly because I really think it is pointless at this point to do well at MMLU. There's so many labs have trained on it, which is unfortunate. And so I often say, well, what is our actual North Star now as a field? And increasingly, I think it has to be private test sets that are not released, which is so unfortunate, but I think that's the case because otherwise we spend all this capacity learning how to do well at MMLU when other models are honestly probably throwing in the test set. Yeah, so it makes us question what does it mean to make progress on some of these things?
I guess like what does Cohere's internal evaluation scheme look like? Maybe even just for its research.
Yeah, we create our own, mainly because we need to preserve our own measure of progress that's not tainted, right? And that way we can evaluate our competitor models and we actually have a good sense. So we have a version of like math and code that is our own, that is not released. But we also have a version multilingual that is our own that's not released. And we also have open-ended. So this is another key important. And typically as we go through the process of developing, we are measuring some of these external, but like our measure of progress in making decisions are the untainted, the ones we know certainly to be untainted. And I would advise for any of your research projects, if you're serious about like pushing the frontier of what's possible, your goal should be to try and carve out that boundaries for yourself. Because, you know, extra 2 points on MMLU doesn't mean anything these days, unfortunately. Or you might end up spending your whole PhD trying to do that the right way, and other people are just throwing it in, which is equally unsatisfying and not really good science. Yeah, that's my grumpy take. Yeah, maybe the last one, and then
Yeah, so you talk about that, you can basically pull out 90% of the model parameters where you give most of the performance instead of those long-tail examples. I'm just kind of curious, like, because sometimes we do want the model to be able to perform those long-tail examples. And do you think there's ways to, because I think from the way you say it sounds like those long-tail examples need such a huge amount of parameters to learn. So is there any way to think that it's possible to use a small model to separately just learn
Yeah, in some ways, like I think the whole idea of cascade models kind of gets at this philosophy. Cascade models traditionally have only been used in production environments, but I think it's interesting to bring them back into research environments. Cascade models are they started off as a solution to like privacy in some ways. There was this idea that, let's say your voice detection, you have a local model. The local model will try and solve what you're asking. If it can't recognize what you're asking, it will send it to like the bigger model that's on the cloud, and that will process it. It was to minimize latency, but there are some components where if possible, in an ideal world, it just wouldn't send your data to the cloud. I think cascade models are a version of this, right? Like you use a small model for the most frequent, and then you pay more in compute if you find something that you're uncertain about. It hinges on us being able to tell when we can't solve a problem. So this is a very fun problem within machine learning, uncertainty calibration. But I think, we know that our models are getting more calibrated over time. We can argue about how calibrated. I think that's worthwhile to discuss, it's certainly not precise, but I do think it's a promising direction, and we should bring it back into research again. There are some research papers on cascade models, but it's not as common as like mixture of experts when we discuss some of these adaptive compute frameworks.
But that's a similar mindset to speculative decoding. Right.
It is, but it's actually like routing the whole example. I don't know if that makes sense. Like you're not, yeah. So yes, if speculative decoding has a caveat where if the drafter is too uncertain, it goes to another, but often the cascade is like multiple levels in the system. I think go to 3 different models. But you're right, there's similar kind of characteristics there. Yeah, if you're uncertain, you are defaulting to a larger model to draft. So yeah, that's a nice point. Okay, nice. Thank you. This is great. This is super fun. Yes.